my original plan was to talk about special triples of points in the plane, and that itself would cover a complete graduate course, not one or two lectures. But let's see, what are we talking about? First of all, I don't know, it's not moving. Something is not right with, okay, now. So, yeah. I thought that we should focus on problems related to rigidity, but that's also okay because rigidity is a very general phenomenon. So you heard Bezout theorem. I think there were some nice lectures on algebraic geometry. Well, a very special view of algebraic geometry, but that covers very similar things. If you say that you have in 3D a two-dimensional surface of an algebraic surface of degree d, and you have a line which stabs at least d plus 1 points, then it suddenly should be part of this surface. So it's very rigid. There are no more flexibility. And in geometry, there are many other examples. And because I will talk about incidences very often, I came up with this example first. We all know Pappus theorem. So if you see, that's for me, it's a rigidity that those points x, y, z should be on a line. To prove the theorem, you can use Bezout theorem, even for conics immediately. It's a 3-line proof, very nice application of algebraic geometry. You don't need that here, but you could. So those things are related. Okay, let's see another formulation of the same theorem, which is somewhat closer to what we are going to talk about. So this is rigidity. When you have a rigidity problem, then, well, for me, the classical question was to have bars and joints. But then I learned that not only joints, you might be allowed to use slides and other objects. I'm not an expert in rigidity. So when I think about incident structures, you have an arrangement of lines, and certain points are crossing points of more than 2 lines. Otherwise, it is not very meaningful. Then you can say that, you know, this is a special place. The lines could move or rotate about this point, but those 3 lines then should be concurrent at that point. So, for example, here at U, if you say that's part of the incident structure, then that's it. It will stay. And then you can ask again various things. What is rigidity? Well, you can talk about the rigidity of the whole system. We will do that probably at the end of the sequence of lectures, but you can ask all kinds of problems similar to Pappus, like here. You see, this is very very simple statement. You have a 3x3 Cartesian product, and if you connect those pairs of points, then the third point on those lines will be concurrent. This is also something relatively easy to prove, but those are just examples. So, okay, it's not moving. It used to be an animation, but yeah. Right, it's not very important. So we will cover probably more than I wanted to, so I can just go further. Here is an important point. When you have points and incidences, then you would think that this is part of geometry. Well, it's definitely, it is part of discrete geometry. But if you wish, then it could cover a huge part of algebraic geometry. I don't know if you heard about this classical construction, the von Staudt constructions to do multiplication, addition, and various things using lines, point line incidences. I won't go into the details. This is just an illustration, but this is a very funny and very interesting subject. So you define a point that's infinity. You have to define x, and then just by incidences, you can add 2 numbers. See the second picture here. There's X and Y. And if you take those incidences, then so you go up to actually any point, and you just construct this picture, whatever is given by those incidences, then you will get X plus Y. And then you can get X squared, and you can get the multiplication. If you want to read more, then there's a beautiful survey on this from a geometric viewpoint, oriented matrix of Jürgen Richter-Gebert. And it goes further. So if you can do such calculations, then you can do much more. Like this is a famous, I mean, this is one of the famous calculations of Nikolai Mnyov, who proved that you can represent any polynomial, and he went much, much further. So this is a deep result in algebraic geometry, but this scary picture is just here to kind of try to convince you that just by point line incidences, you can go as far as you want. And there is another wonderful paper of Ravi Vakil, who says that Murphy's law will hold for certain objects. Well, we don't go there, but yeah, we will do something much, much easier. So this is the plan. So much easier, but open problems. So I don't know how to really say something is easy, not as advanced like advanced algebraic geometry. And to understand those problems and even the proofs that we are going to see, those are not extremely advanced. So hopefully it will go very well. And at any time, if you have any questions, then please use the chat or just ask it directly. Unmute yourself and ask the question. So point sets, and we will stay most of the time on the plane and just the real plane. Maybe we will switch to complex plane time to time, but just for fun, because that's a tool, that's a very useful tool for certain geometric problems. So you have a point set, m points, finitely many points on the plane, and you observe that there are many lines which have at least 3 points on it. And many means that if you have m points, then you have c times n squared, collinear triples. Well, not only c times n squared collinear triples, that's easy to have if you have all of them in one line, but that's not what we count. We count the number of lines which have at least 3. So the lines which contain only 2 points, those called ordinary lines. And we expect some structure in cases like this. But how to find it? It's very hard. There is a beautiful result of Terry Tao and Ben Green, but that's a really heavy stuff. If the number of ordinary lines, so the number of lines which have only 2 points, is say linear or a little bit more than linear in M, then there is one particular construction which can do that, but then it should be that construction, an elliptic curve where you can have many collinear triples. If you ever worked with elliptic curves, then you know that there is a nice group structure you can find, and those will define you nice collinear triples. But that's a very extreme example when you have almost all the lines defined by the point set containing at least 3 points, right? So only a linear number out of the n choose 2, well, possible lines. Then a general thing, more collinear k-tuples, that's what can we say in general for bounds or structure, but we are very far from structure if well, many lines have not only 3, but so this is Semeridi-Trotter theorem. I'm just saying that we will see that. And many triples similar to a given triangle. So you have point sets, and here is your sample triangle, and this point set is full with triangles similar to this one. There are many, many triples. Interestingly enough, here we will get a result, but it has something to do with problems in number theory and even problems in harmonic analysis. So the inspiration for this part came from a classical paper of Ned Scott and Terry Tao, where they gave new bounds on certain Kakea or Bezikovich sets. We won't deal with Kakea problems, although that's also related to incidence problems, but yeah. So what can we say when you have many triples? If you have many triangles, and here many means that there is a C that if more than C times n squared, but there is a particular C, n squared such triangles are there, then there is some grid structure you can find. But under the C, you will see nothing. I will, of course, tell you more details on that. And the last question, which we will briefly review first, is that what are the point sets which have many triples which define a unit circle? Okay, and let's see this one first, because this immediately will show us something about rigidity and maybe application of not combinatorics, rigidity for proofs. Let's see. Yes. So here is a theorem. I knew the reference, which I don't know now, and somehow all Google searches failed badly. I did find some exercises asking the same question, but it has a name, and I thought that this is John's theorem. Apparently not. If any of you know what is this, then please let me know. It was rediscovered several times. What is the statement? The statement is the following. Right. The statement is the following, that if you have a point, in this case, that would be B, right? And 3 unit circles incident to this point B, then the 3 other intersection points, in this case, it's H, G, and F, denoted by those butterflies, or I don't know what, those are also on a unit circle. Do you know how to prove it? I don't remember the name. But what do we have here? So here I will switch to, if I can, then I switch to an application. How to do that? I stop share at this point, and I will come back to this point, but I can animate a little. And yeah, the green Tau paper, thank you, Mira, is in the chat now. And I have to begin share screen again. And now we are here. Okay, and I hope that I can do what I wanted. So here is a circle, look at this. I can move it. I can move this. Well, it doesn't matter which one I move. Right, and here is the test. So wherever I move, then the 3 intersection points, what's happening? Oh, yes. So the 3 intersection points are on a unit circle, you see? Right. So in the meantime, I did lose some of the lines, but doesn't matter. So what is the proof? You see, the proof is very simple. If you check those, so here I have, how can I draw? Can I draw here? No, sorry. Sorry about that. Just a second. This is not the deepest part of what we are doing. So let me go back to the Acrobat. That's the safe thing. I want to share. Next time I will use the video. So if you go here, then I think there is a way to draw. Yes, or not. Yeah. If you see, there is this cube, flattened cube, this vertex A, F, D, B, E, and G, and H. And now this is a framework, because all those distances are 1 and they will stay 1, which are there. And the vertices are all, well, we see 5 of the vertices are joints. And all what we do now is that we can add the hidden part of this. Well, I will do my best with my drawing, right? And this is a flattened square or a projected square, but in a way that all the length of the sides is still 1. And this is important. Well, I will do something more important than this in a minute. So if you have, say, first a square, then of course it's not rigid as a framework. And if you have a cube that you can still push down and you can move wherever you want. So here is your push down square, and this other vertex here, this should be the center around the 3 points. This is a unit circle. So this is, well, it was somewhat slow, but this would be a proof by picture that those 3 are together. Now, why is it important? Because this is the best construction I know. In this way, for what was the question? What is the maximum number of co-unit circular triples? I will use the word unit circular. That means, I mean, okay, doesn't matter. And it should be little n squared if you have n points. It can't be constant times n squared, but I can't prove it. And that's a very old question. And if you can prove this one, then this would also imply a partial result on a very famous conjecture, a very old conjecture of Erdős, Paul Erdős. Maybe you know that the distinct distances conjecture was almost completely solved by Katz and I know him very well. At MIT professor, I don't know. He wrote a beautiful, good, yeah.
This is Dwyer? No?
No, Good. Larry Good and Ned Katz. Dwyer was the pioneer to introduce the polynomial method, which is a fantastic method and should be used, and we use it in geometry, but that's another method. Sorry, so where were we? If you could prove that the number of circles with at least 3 points out of your point set, so the number of triples, but I don't count if they are on the same circle, because otherwise you just have one circle with many triples. So if the number of such triples is little n squared, that would give you a breakthrough result in a more than 50 years old conjecture of Erdős. Right. So I don't know how to prove little n squared. And the best construction I have, if you do this, if you just check this theorem what we had here, that if you have 3 unit circles, then their intersection, 3 intersection point will also give you a unit circle. So take n circles incident to a point, they will give you n choose 2 intersection points and n choose 3 points. So the bound we have is n to the 3/2. So there is a construction, this construction, that you can have n to the 3/2 co-unit circular triples, but nothing better is known, and it's not even known that it's little n squared. Okay, so again, I don't know. For some reason, it won't go any further. What do I do wrong? If I use this one. Okay, so that's just a puzzle, and we leave the unit distance bars. So this, with my student, we answered the question that was, so it's still rigidity. That was a question, I should erase this one, of Malhara. He asked if there is a rigid unit bar framework with no odd cycles. So that means that this would be a bipartite graph, if there is such thing. what do I want to do? I just want to erase what is there, sorry. This one, yeah. Good. And well, we find one, here is one, but we don't know if this is the smallest or not. So here is the challenge, that find a rigid bipartite, so there's no cycles, bipartite framework. All the bar lengths are 1 and rigid. So this is the smallest we had, but this opens also for our problems where we applied, or we are planning to apply rigidity, we have given side lengths. So we don't have this nice situation that we can talk about some kind of algebraic independence or anything like that, generic framework, no. All the distances are given. That makes stuff, yeah, as you can guess, that's immediately another ballpark. We need different techniques, so yeah. Good, so let me go further, and for some reason it's very complicated to switch. Yeah, so this is the triangle part. What can we say about point sets when you have many similar triangles? I think that's the thing. Well, that's the subject I have time to talk about. But this will be an example to the connection of extreme graph theory, additive combinatorics, and geometry. So maybe this is interesting. So this is, as many of the problems I'm going to talk about, originates from Erdős. And Erdős and Delekes unit distance conjecture solution, sorry.
Can I stop you for a second, Jozsef?
Yes.
Can you go back to the slide where you had the circles and you mentioned that you had a problem there? Could you just state that problem again? Yeah, this one.
Yes.
You said you had a problem there that you want an answer to. You didn't mean which.
What is the maximum number of triples from unit cycles on endpoints? So okay. The one sentence which is missing, that from endpoints. Okay. Otherwise, the title itself.
Okay.
And there is this link. Someone said that unit distance conjecture of Erdős. Anyways, that's on the.
I couldn't find a Wikipedia page or something. I just found an archive paper whose abstract describes the problem, so a conjecture. So I just put it there.
Mm-hmm. Okay, I will check. I think somehow Wikipedia has another label on that problem. Yeah, okay. Good. Thanks. So is it clear what is the question here? The lower bound, what we gave by this rigidity example, which gives n to the 3/2, because you have n circles, they will give you n choose 2 points, or the pair, well, 2 times n choose. No, n choose 2, because the middle won't count, yes? And then any triple will give you a circle, a co-unit circular triple. So that's, so the ordinary points, I don't know what are the k ordinary points. There was a question of unit circles. Right. So yeah, but this is a wonderful problem, and I can't say much more about it. All what I can say is that, yeah, that it's n to the 3/2. There is another related question. Do you want me to have more questions, or let's try to?
Sure, yeah.
More? Okay, here is a question. It's rigidity, and it's in the same family. So you have a unit bar length framework, what is the number of bars you need to guarantee that there will be at least any rigid part other than the bar itself? So let me repeat the question, because also if you can solve this problem, that would, well, I know a way that that would also break this famous Erdős problem, which is, yeah. So let me repeat, sorry, it's not written. Or I can, you know what, I can switch to camera, and maybe that's not a bad idea at this point. If there are no objection, then let me stop. Those similar triangles are interesting, but maybe not that interesting as what we want. So let me just write the questions for a second, okay?
So I put something in the chat.
Yeah, but what do you think about this one? It's okay. So yeah, you put something on the chat, but what are the questions which would break problems which would improve the Erdős unit distances? Conjecture, conjecture. Among endpoints, we are on the plane. There are at most n to the 1 plus little o 1 pairs of points at distance 1. And you can't really expect n, because if you see the integer grid, then that would give you something more. It's a little bit of number theory. You just choose, well, the integer grid itself is not, but if you scale it down. So if you take an integer grid like what we have here, then you take a k, which has many ways to write as a sum of two squares, and then, of course, those circles would have would contain many points. Anyways, this is the conjecture, and I want to give you two problems which would imply an improvement, because the best what you have at this point is so currently best, which is an ancient old result, is n to the 4/3. That you can't have more than some constant times n to the 4/3. And there are very simple constructions for that. I could show you some, but that's later. So the first one, what was the problem we had? So among n points, this is the kind of among n points, what is the maximum number of triples, point triples, with by defining unit circles? And you don't count a triple, I mean, you only, from any unit circle, you count only one triple. Or you can say that what is the maximum number of unit circles which have at least 3 points going through. So maybe that had something to do with the question on ordinary lines or points or other things. And the construction we had was very simple. You take n circles, and armed with the result, you know that for any tree, the intersection is a triple which defines a unit circle. So lower bound, best known bound. The best bound is n to the 3/2 with some constant The constant is square root 2/3 if you are interested. I can't even improve the constant which comes from this. Okay. And the next question, that was more like a rigidity question, which would improve the unit distance conjecture bound immediately. It comes from, it's the following, that what is the minimum number of unit, I write unit bars, but so unit distance bars. You can use only one length bar in a joint. So a simple planar joint bar framework that if you have that many bars, then so that it contains a rigid part. So at least a triangle. Well, triangle you can't really guarantee by less than n squared contains a rigid part. Is it clear what is this question? Because this would be fantastic. What's the lower bound? What do you think? So rigidity usually, well, if there is a proper genericity, then it's a linear bound. But no, here you can easily get n times log n. Any ideas why? Anyone? Because we had this example already.
I don't understand. Why can't you use 5?
You can use 3.
Triangles next to each other. You get a pair that's rigid besides the
But
bar.
here the question is that what is the minimum number of unit bars that will guarantee? It doesn't matter how you put them together. If you have that many bars, then there is a rigid part.
Oh, it's for any arrangement.
For any arrangement. But yes,
Well,
you're right. I should have
You could put
emphasized
unit
that.
bars down at random and there's no.
Random
Is there
random
something
will
about
be
the frame?
rigid, but I'm not saying it's random. It's very not random. Even the example that I'm going to give you is not random, which gives you at least a lower bound of n log n. And I don't know a better bound than n log n.
Why can't you do it with 5?
I could do it with 3. This is rigid, but this is not the question.
Well, I don't understand the question.
Thanks for asking. The question is, what is the minimum number? So this is, let's call it M, okay, capital M, N. So the statement is that for any joint bar framework with the unit length bars contains a rigid part. Okay. So
What does that mean?
what?
I just don't understand what that means.
It means that the devil will construct from your tools. So I give the devil that many unit bars and joints, and the devil will keep it flexible without any rigid subpart as long as it's possible. And if so,
excuse me, Jozsef.
Yes. Yes.
The point is that there's n joints.
And joints.
And we're given n joints. We're to come up with this number m of unit bars so that
Yes.
no matter what way we place those M joints, those M unit bars among the N joints, there will always be a rigid
Yes.
part. Mhm.
Yes, thank you very much for saying it. And probably
At
I
least
was
as
so
big as a
excited.
triangle.
Sorry?
At least as big as a triangle. I mean, at least 3 vertices, right? You don't mean 2.
No, 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 no. I mean that any framework on n vertices, I say, but you understand that's the number of joints and joints. So that's the number of joints one can use with mn unit bars contains
Oh,
a rigid part.
And the rigid part has to have at least 3 vertices, right?
Well, yes, because that's the joint itself, yeah.
Yes.
I mean, the bar itself is not interesting for us, yes.
And you don't expect 2 vertices not connected by a bar to have a fixed distance because of this.
No, that would be also something. That would be, yeah, that's also interesting. I didn't say that, but now that you are, yeah, that would be also very interesting. Even if you can say that there are 2 points without a bar
Yep.
between
That the
them,
distance is fixed.
if you keep the distance the same, that's also, that would also work. It's not a simple work afterwards, but this is where I lost my track on improving these problems. And this is, I think this is a nice question for.
what is the
on
construction? What is the
rigidity.
construction?
Oh, the lower bound. So there is a, we can see that this is at least n log n. And the construction is something what I said before, but yeah, so take a high dimensional unit cube. This is in high dimension now, but squeeze it down. There is nothing against it, and it will be a planar thing. So first you have the square, yes. That's of course not rigid. Then you have the cube. That's of course not rigid. Then you have the hypercube, and you can squeeze those things down without changing the length of the bar. So that's a planar object, and it goes everywhere. So the degree of freedom will be actually the same as the dimension. I mean, -1, right? So this is a recursive construction. If you have already part which is not rigid, and you take another one, a copy, you just translate it by 1. If you don't like this hypercube example, you just translate it by 1, and you like by conjecture, you just connect the corresponding points with those. Then it's still not rigid because you can move them, and they were not rigid there. So, and if you repeat this method, then that's exactly log n log n. So the number of edges will be, the number of unit bars will be n log n. And that's the best I know. I'm not brave enough to say that this is even close to the truth, but that's where we are. So add the unit distance problem. One should be careful because there are many constructions, or I mean, there are many examples where your distance is not quite the circle. It's another curve, like the parabola. And there you can have n to the 4/3 unit. So fair warning, we really have to use here, for example, well, that's why I like this, framework formulation, because here you can't change the length of the bar. But if you have a, you know, any central symmetric convex body, could be your unit circle if you wish in geometry. Let's for a second forget this one. Then if So if you have the y equals x squared parabola and you cut it like this, and this will be the lower arc and the upper one. So this will be your so-called circle. Now, the center, if this is your unit circle, the parabola thingy, which comes from this arc, and you flip it, then there are easy constructions for n to the 4/3 so-called unit distances. So points where with this measure, with this distance, there are n to the 4/3. Right.
So so when you do these constructions, what you always get that you're saying the distance between any pair changes?
No. This one here, sorry.
Yeah.
No, here this is convex geometry. You have the freedom to say for any central symmetric convex body that this is your unit circle from now on. And then you just work with that. For us, or for the definitely here, it doesn't matter what is the angle of your bar, it will be always the same length. So what I'm saying is that in Erdős unit distance conjecture, it's very important that we are really talking about the Euclidean distance 1. If you modify it just a little, then you can't aim for n to the 1 plus little 1, because it's suddenly n to the 4/3. There are examples for that. Those constructions follow from Szemegy-Trotter's theorem, which I'm going to explain. But yeah, but let's go back here because I really want to say a few words. This is one of the most intriguing, interesting open question in discrete geometry. One, the distinct distances was solved already. There's no hope, or there's no tool. We can't do anything here with the unit distances problem. Okay, any questions here? Because I see that my time management was awful. I have like 15 minutes.
So
Yes.
can you briefly connect the unit distance problem or any of these variants to the original problems that you started out with collinear points, number of collinear points, etc.
So yes, those constructions come from, but so that's not really the unit distance. That's the best bound which we can give as an upper bound that comes from these incidence bounds. And maybe I can, so I still have like 10, 13 minutes or so.
Yeah.
About. So let me write here
we started about 3 or 4 minutes later. So yeah.
So what I'm going to do now, I will state an incidence bound. This is a very important tool. Whenever you work with point line incidences, then this is important. So let's see the authors. This is a theorem of Szemegy and Trotter. And it captures the difference between the real plane, the Euclidean plane, and say finite fields. So just the definition of points and lines from the axioms. So like in finite geometry. So what is the statement? For the sake of simplicity, let us suppose that the numbers are nice. So we have n points and m lines in the plane in R2, okay? And what I said that they are nice, that say n is at least is between square root m, and m squared. Yeah, so they are not very far from each other. Otherwise, there would be an easier, a trivial bound. But let's say that they are in this range. Then the number, so we have n points, m lines. The number of incidences, what is an incidence? It's just a point line pair where the point actually lies on the line. So the number of incidences is smaller or equal than some constant times n to the 2/3 times m to the 2/3. Now, if you don't have a Euclidean plane, then you can't state such a theorem. It would be just the kind of obvious bound that through any 2 points, you have only one line going through, and for any 2 lines, you have one intersection point. So then this bound would be a much weaker bound. It would be square root of one times the other, or this times the square root of the other. That's much weaker. This is due to the structure of the Euclidean plane that you have a better bound. But before that, let's just see the incidences to be sure. What is the number of incidences here? So the number of incidences is 6, because for every line you count every point. So here you have 2 lines going through 1 point. So the number of incidences here is 6, just to be sure that we understand the same thing. What are the incidences? Okay, you can reach this easily with lines on the integer grid. Choose your parameters n and m, and then you will find an optimal richness here, which will give you this bound exactly. So you can achieve that many incidences, but you can't have more. Right. Now, armed with this tool, yeah, we can prove various theorems, but before I go there, let me say that we don't really need lines. This is also true for pseudo lines. So if you have on the plane, strictly on plane, some curves which have the property that any 2 has no more than 1 intersection point, then you have the same bound. And it's easy to prove. I won't prove it in 5 minutes now. I just want to use this theorem. We will see the proof of this theorem because it's a beautiful probabilistic proof. But again, what is the theorem? If we have n points and m pseudo lines, then the number of incidences between those pseudo lines and points is not more than n to the 2/3 times m to the 2/3. Okay? And what happens with the unit distance problem? So let's go back to the unit distance problem. For every point, we have n points. For every point, you draw a circle of radius 1, a unit circle, right? And well, how many points you have on this circle, that will give you that how many points are at distance 1 from this point, right? So we have now n unit circles. And those will be our pseudo lines. Well, they are not quite satisfying that any 2 has not more than 1 intersection point, but we can cut them into 2 halves, the upper half and lower half. So if they are pseudo lines now, as we want, and we can apply the Semeridi-Trotter theorem, then it means that the number of incidences is smaller than we have n points, because all those circles are on points, n to the 2/3. And around every point we had a unit circle, that's also n to the 2/3. So this is n to the 4/3. So we have this, this is a very simple theorem to prove. I just don't want to do it right now. But the statement is that on the Euclidean plane, it's true that among n points and m pseudo lines, which are any curves under the condition that any two curves have no more than one intersection point, the number of incidences is not more than n to the 2/3 times m to the 2/3. Based on that, we are done. This is the upper bound, n to the 4/3. Well, we are not done because this is the best we can come up with. This is very far from n to the 1 plus little 1, the conjecture. Right. Now, armed with this, so this also tells you or shows you possible constructions where the number of unit distances or so-called unit distances are of this number. Let me give you a very tricky two constructions. Maybe I have time. So one observation is that here, what do we have? I told you that even with lines, there are lower bounds which really give you this bound. So if we have n to the 1/3 rich lines, what is it? Those are lines in an n in a square root n by square root n grid. We have the integer grid, so this is a nice grid. And we take all those lines which contain at least n to the 1/3 points. There are n of them. You can count them by number theory, or, well, there are easy ways to count them. So now what we have in this construction, we have lines with n to the 1/3 points. If they were unit circles, then that would be a counterexample. They are not circles, but what can we do? The construction, what I'm going to show you is what I promised, that if you have this different unit circle, which is from the y equals x squared, you go up to, say, a certain part of it, and then you flip it. So if this was your unit circle, in convex geometry, you can just say this is a central symmetric, nice, smooth. It's not conditioned that it's smooth. Anyways, so if this is the unit circle, then you can have n to the 4/3 unit distances. How? So we are here, and we will apply now a transformation, right? So for every point x, y, we transform it x, y plus x squared. Right. What will be the image of a line? If you see under this transformation, every line from here, I don't want to begin a new page, so I throw it here. Please forgive me for the mess. Next, it will be slides, but I deviated a bit from the plan. So all of them will be nice parabolas. All will be translates of the y equals n squared parabola. And you see, instead of unit circles, now we have parabolas containing many, many points. So if you want to come up with some combinatorial rough proofs using intersections or something, it won't work. You can't go below n to the 4/3. There are beautiful examples like this. But there is a, in my point, I think it's an even scarier construction, just very briefly. On a sphere, I can give you a point set where the number of unit distances is n to the 4/3. And you would think that whatever I can do on the plane, I can do that on the sphere. Well, here's an example. You have the same construction what we had. What did we have? We had n lines, each n to the 1/3 reach. That means that it contained as many points, yeah? So here, containing many points. And you have n points. And what you do that you place here a sphere. above. So it's like the plane and a plane, and on the plane now you place this nice sphere, which will touch the plane. See the center? And from here, whenever you see here a point, then there is a line connecting and this point, and it will stab the sphere at one point. Now this will be your point set on the sphere. Almost. So if you have one line here, that will give you somehow a great circle. The points will be on a great circle, right? Because through the center, this line, that would be a plane cutting a great circle on the sphere. Agree? So I add one point. I add the North Pole to this great circle. How many points did I add? So I added the endpoints from here, and for every line that were end lines, I added the North Pole. But from the North Pole, the distance, if the sphere was the right size, from North Pole, every point along the equator are at the same distance. So this will be your unit distance. So with this construction, again, you have n to the 4/3 unit distances on a sphere. So there are constructions showing that there is no easy way around the unit distance problem. At least it doesn't seem to have any way around. Right. And I think the time is up. So this wasn't really my plan to go like this, but definitely I was able to tell you one problem, the unit distance problem, which is one of the major open problems in discrete geometry. At least I stated an incidence bound, the Erdős-Szemerédi, the Szemerédi-Trotter incidence bound, which we will see, because that's something we want to see in details with proof.